We've seen that definite integrals are used to obtain areas under curves, and before we go through methods to evaluate them, we'll look at some basic properties of definite integrals. So if we integrate a constant multiplied by a function, then we can take the constant outside the integral. And the integral of the sum of two functions, or the difference between two functions, can be broken up into two integrals. So we integrate the first function, and then we add or subtract the integral of the second function. And we can also reverse the limits of integration. So if we integrate from a to b, we can negate the integral and reverse the limits. So in other words, we can integrate from b to a. And we can also break up an integral into several integrals. So for example, we have a piecewise linear function. So suppose I want to integrate from 3 to 5. I can first integrate from 3 to 4. And that's going to give me the area under the curve from 3 to 4. And I can continue the integral from 3 to 5. And that's going to give me this area under the curve. So in other words, we integrate from a to c, and then from c to b, to obtain the area over adjacent intervals. We can also use definite integrals to find areas under curves where there's removable and jump discontinuities. So to find the area under the curve from a to b, we can still apply the definite integral in the same way, because as you can imagine, even though the function does not exist at c, the area at a point is infinitely thin, so it's not going to affect the result. Now with a jump discontinuity, we can evaluate the integral piecewise to find the area under each curve to both sides of the discontinuity. So we can integrate from a to c first. Then we can add the area from c to b. So to obtain that, we'll integrate from c to b. And later when we evaluate improper integrals, this limit of integration can be replaced with a dummy variable, and then we take the limit as the dummy variable approaches c.